So this is a video demonstration for Lab 8. Our team consists of myself, Rohit Kane, Farahanaaz Shaikh, and Kautuk Patil. So we'll go through all the files one by one and give a brief explanation of them. So firstly, this is the Verilog file for the pipeline. This is based on the pipeline diagram which was provided in the PDF. So here we can see that we have created multiple registers, stage registers, IFID, ID, EX, EXMEM, and EXWB. So after that, we have instantiated the memories, the I memory, the register file, and D memory. So later on, we like based on the diagram and all the control signals that go from one stage to the other, we basically routed the signals, control signals, and the data as well as the addresses from stage to stage. And yeah, so that is the Verilog file for the pipeline.
Now let's look at the memory blocks. So we used our own memory configuration for data memory and instruction memory. This is the data memory. Here we have the depth of 8 bits, that is 256 total depth, and it is 64 bits wide. So it's a simple program where, depending on write enable signal, will write on to the memory, and data out will always be assigned as a non-blocking statement from memory. And then we have instruction memory, which is similar in pattern. Here the depth is 5 and 2 bits, and the width is 32 bits because our ISA is 32 bits. And the write structure and the read structure is similar to them. Now we have written a test bench file. Over here, we are calling the pipeline.read design under test, and we have given signals, clock, and reset. Now we are also calling the text files, which is basically the instruction memory and the data memory. So when we take a closer look at it, here we have several no-op signals and several useful signals. Like at first, I have written to read data from the memory to the register. That is basically a load operation. And there is certain store operations which is performed on different parts of the memory depending on the address. Now, data memory consists of some values which are pre-stored to it. So the first content, for example, has the data 01, which we will use in our example. And the second location consists of data 0. Now, when we look at the simulation, here, my program counter PC is being incremented in each cycles. So first it was loaded with NOAA, and depending on each register, it goes on to several data. Now, when we move ahead in the simulations, we can see the contents of register file, the main memory of our internal registers, that is being updated. So the location contents of register file at location 2 and at location 3, as well as register 0, is being updated in these cycles after certain time duration. So 1 clock duration later. Now, similarly, after the write operation into the memory, we can see that the content which was earlier memoed was 01. But after just writing to the value, let me just zoom in. Yeah. So earlier this value, if we look at it, it was 0F for the same memory address. So when we look at the address which was provided in this location, it stays the same, but still your data is updated to 01. So that is how we performed load and store, basically an operation which doesn't require ALU. Now we'll look at the ALU design for this.
Yeah, so basically we have written a Verilog file for the ALU, and the ALU operations depend upon the ALU CTRL control signal, so which is basically a 4-bit signal. So later on in the file, we can see that based on the case statement of the ALU CTRL, we perform multiple operations. As you can see on the screen, that first operation is addition, subtraction, all that was specified to be done. And yeah, so then we So now we'll see the test bench for the ALU. Yeah, so then we toggled the ALU CTRL for performing various operations on the data, which is A and B, and that can be seen, the output can be seen on the Z. Yeah,
So
on
the
the Z.
first output is doing addition. So you can see the last bit, for example, 0 plus 9 is given out to be 9. But in the second operation, it is doing subtraction. So 4 minus 1 is equal to 3. And similarly, all other operations were verified. We can also look at the simulation of register file just to verify that it is working properly. So when we zoom in, basically we have written data into several locations using write address and write data. And using the two channels for read board, we can see that several data has been accessed based on what is written into it. So at R0 data, you can see some data popping up. It's corresponding to the address 01, which was written at this location. So we can see that the data which was written into is successfully can be read out. Now,
Yeah, we then synthesized the design and generated a bit file, and then later on we downloaded the bit file on the NetFPGA control node, and then we pinged all the nodes in the design, and as you can see on the screen that all the nodes were up and running post the synthesis.
now to interface it with the instruction and data memory, we updated the IDS.xml file. So for that, we have several software registers. For example, for using read addresses, we have declared it as a generic software. But for data memory write address or for data in general, we have written 32-bit system. Now our data memory is 64 bits in width. So we have split it up into high register and low registers. Now these registers are initialized in the IDS.v, and then it can be used easily using the Perl interface. So we are using IDS reg itself. Now here we have declared the registers which are needed for us: the data memory data high, DMEM data low, and read address and write addresses for each of the instructions. And we have declared functions which is basically memwrite and memread, which will give the command of what operation needs to be performed and the address corresponding to it. Based on that, the value will be written or read from it. Now, similarly, we have a function for reset, which will basically reset the entire instruction memory to all zeros at the start. So after this, we tried running other couple of strings. So first thing is that without changing the IDS user data part.v, we tried changing the IDS.v, and we needed access to the instruction memory and data memory instantiations. So our approach was to write down the pipeline.v code into the IDS.v. So here I've instantiated the module and the registers required. And then these internal wires have been declared so that depending on whether we are in configuration mode, saying that we want to write to the register, so we can do all of these over here. So I've written a separate part into the same always block, and depending on the command, which is processor underscore CMD, depending on command, several other operations will be performed, like writing to the instruction memory or reading from instruction memory, then writing to data or reading from data memory. Also, there is other function which is to initialize all instruction memory to 0. So that there is no corruption of memory happening. And the else logic is our conventional pipeline code. That is, whatever registers are passing out the data should proceed as is. So this is the IDS.v. Now here, if we look, we have made changes to the IDS.reg.perl file. So based on the bit file generation and the registers which have been allocated, I have accessed and written out the variables here. After this, there are certain functions which I've written. One is instruction memory reset, that is to reset all instructions to 0. And since processor underscore CMD, this register is a hardware register, we can store values into it if we want to. That is the plus point of it. Then we have a processor normal mode. So that is to run the pipeline.v, the pipeline flow normally, once we are done writing to the instruction and data memory. Then there is a function called imem, right? That is basically instruction memory it's written. And it is based on the values which are passed to the address and value. And that corresponding values are written, and it is then accessed in the IDS.v module. Then we have data memory write, which is similar to instruction memory write. After that, there is imem write function, which is basically taking address as the input, and the corresponding data is printed out on the statement. And these all functions have been called upon in the argument section. So if we have the string present on our command, we can access these registers and these functions specifically. Now here, I've downloaded the bit file. So I've downloaded the latest file, which is today's. And so if we log into the nodes, I've made access to the nodes, and we can see that it's running successfully. This is a TCP server client connection, and it has connected successfully to the ports, and it transfers to the max speed. So that verifies our assumption that IDS.v was isolated from the pipeline processor. Now, when we try accessing the IDS registers, the initial ones, which is basically reset, so that is done successfully. We can write to the memory. So this would be my address, and then I'll follow it by the data which I have to write. And you can also read it, but currently a read functionality is not working well. It's showing some random jargon data, and we still need to figure that part out, but rest of the things are working is what our assumption is.